Okay, hi everybody. Thanks for watching this little video here. It's on an iPad, so the focus may be a little issue, so I hope you can bear with me. Anyway, here are the solutions to the practice quiz today. This right triangle is maybe the weirdest one on the whole problem, or on the whole test. This is basically the length of the short side, 5 root 3, and the long leg, or sorry, the hypotenuse is 2 times that, or 10 root 3. But I thought I might want to illustrate a little bit how we got to this 5 root 3. If we have a 30, 60, 90 with the long leg given, you know that this short leg here times the square root of 3, all right, is going to equal the long leg. So if you have that little equation right there, y times root 3 equals 15, you solve it for y and you get y equals 15 over the square root of 3. All right, so that's pretty easy, but that doesn't look like 5 root 3. However, if you take that fraction and rationalize the denominator with this little trick that we've practiced a few times, not too often, multiplying the fraction by that same radical over itself, okay, the one in the denominator, this fraction of course equals 1, so we're not changing the value of that fraction, but what we end up with is 15 root 3 on top over, and then root 3 times root 3 just equals 3. So 15 root 3 over 3 simplifies down to just 5 root 3. And that's where our 5 root 3 comes from. Okay? So back to the quiz here. We got that number. These other ones I think are a little bit more straightforward. If the hypotenuse is 7 root 2, then the two legs are 7 on the 45. Here's another 30, 60, 90 right triangle. A equals 7 and the long leg is 7 root 3. 1 root 3, 2. Okay? These two triangles down here, you got to use a calculator, and I chose to use inverse tangent, although since all three sides of the triangle are given, you could use you could use inverse sine or inverse cosine as well, and get the value of theta. It should always be the same, of course, 63.4 degrees. This one, using the cosine of this angle, cosine of 55 is 23 over x. You solve that equation, you get 40.1. Okay, so then these exponent problems down here, I've got 3 times m to the negative 4th over m to the 3rd. Well, negative 4 minus 3 equals negative 7. So this is 3 times m to the negative 7th, but since I don't want any negative exponents in my answer, I write that as 3 over m to the 7th. This next one that's got all these things going on in the fraction, just handle one thing at a time. The 2 over the 3, well, that doesn't simplify, so it's just 2 over 3 still. H to the 3rd is on top, and there isn't any other h's in the problem, so that doesn't change. Then I've got j to the negative 3rd over j. So I'm handling kind of like the variables over themselves, one at a time. Well, negative 3 minus 1, right? We subtract exponents. Negative 3 minus 1 is negative 4. So that means we have j to the 4th in the denominator of the fraction. Okay? And then k to the 4th over k, well, 4 minus 1 is 3, and it's positive, so it stays right up there in the numerator. Okay? Next one, 2 times 2 gives me 4. X to the 3rd times x to the negative 1 gives me x squared, and y to the negative 3rd times y to the positive 3rd. No more y's. It's actually y to the 0 power, but we just write y to the 0 as a 1 and don't even include it in the answer anymore. Next one is also kind of tricky. Several different ways you can do it. What I did in this method here was to say I applied or distributed that exponent to each of the terms inside the parentheses. So that's 2 to the negative 1st. It's not 2 times negative 1. It's 2 raised to the power of negative 1. And then I do multiply these exponents together. So 4 times negative 1 is negative 4, and negative 3 times negative 1 is positive 3. So y to the positive 3rd, that's going to stay, you know, it's like this whole thing is over 1, right? So that's going to stay on top, but these other ones with the negative exponents are going to flip down to the bottom of the fraction so that they have positive exponents. And that's what it looks like there. The quadratic equations, pretty straightforward here. These weren't too tricky, I don't think. Just make sure you get all your numbers correct. This gives you negative 23, 5 and a 6. Don't simplify it all. So 5 plus or minus I root 23 over 6. That's your answer there. Pretty much done in one shot there. This one has a little bit of simplification going on. So b squared minus 4ac, that's 100 minus 4 times 2 times 6. That's 100 minus 48, which is 52. And 52 is 4 times 13. So the square root of 52 breaks down to 2 root 13. Well, I got a 10 and a 2 and a 4, all even numbers right there. So I'm going to reduce all of those by a factor of 2. And so I end up with 5 plus or minus the square root of 13 over 2. Okay, let's talk about those proofs, huh? All right, here's the proofs. Now, there's definitely more than one way to prove this. As we talked about this throughout the day in other classes, people came up with other ideas. My strategy was to show that these two triangles are congruent by angle, side, angle on each of them. I've got alternate interior angles at these corners and at those corners up there. They're congruent. I've got a congruent side in between those congruent angles, so I've got angle, side, angle. That's what my paragraph shows, and you can read my paragraph. But other people have shown that since the diagonals of a rectangle bisect each other, which is certainly something that you could use, you can say that this segment right here is congruent to that segment right there. We've got congruent angles right here at the vertical angles, and then and we've got congruent angles here and here. So you could say angle, side, angle, using that piece of the triangle. Again, you could even say side, angle, side, because these are also congruent. All right, the diagonals of a rectangle bisect each other, so you could go side, angle, side. So angle, side, angle is away, side, angle, side is away, and you could even make a perfectly tight argument by saying side, side, side. Both of these are congruent since they're being bisected, and these two sides are congruent as well because they're part of a rectangle. So there's actually several different ways you can prove those triangles are correct. You just have to have your sentences nice and clear and with all the proper features of the diagram named. All right? And as long as you got that, we have as much flexibility in proofs as we do in our language, all right, which means a lot. The next proof, I think there's not quite as many ways to show this, but again, congruent triangles is kind of what this proof is based on. So I've got, I'll read it to you. Since ABCD is a parallelogram, we have parallel sides cut by a transversal, and angle 1 is congruent to angle 2. Okay, that's because they're being alternate interior angles. It is also true that opposite sides of a parallelogram are congruent. So that side and that side are congruent. All right? And it is given to us that FC and AE are congruent. Therefore, we can say congruent, congruent angle in between them. Side, angle, side. All right? And that's how I'm proving that these two triangles are congruent. All right? Therefore, we have side, angle, side, triangle congruency for triangle DEA and triangle BFC. Since congruent triangles have congruent parts, side DE is congruent to BF. That is kind of the core of the strategy, folks, is to show that if you have congruent triangles, you have other congruent parts of those triangles. So my strategy was to show that these two triangles are congruent to each other. Therefore, these two corresponding parts are congruent as well. Okay? Sorry, I'm at a weird angle there, aren't I? Okay, good luck with that. I'll see you when I see you. Thanks for watching.